Hello, welcome to the unit on transformations. This is unit 11. We're going to be working in section 4.8, parts of chapter 4 and then parts of chapter 9. So first of all, I'm going to give you the definitions. I will pause towards the end so that you can pause and write them down. Transformation is an operation that moves or changes a figure in some way to produce a new figure. Do something to the figure to produce a new one. The new figure is called the image. The original figure is called the pre-image. Make sure you get that terminology down. Image is the new figure. Pre-image is the original figure. Prime notation is triangle ABC goes to triangle A prime, B prime, C prime. So this little mark right here is read as prime. That is the notation for prime notation. As you can see right up here in this little example, sometimes they use different letters. Triangle ABC goes to triangle PQR. ABC was the original figure, also known as my pre-image, and triangle PQR is the image. It's my new figure. So when I am writing prime notation, if they didn't give me new letters, I keep the old letters and I put A prime on there. If I were to move it twice, then it would be A double prime, and I would have two little marks instead of just one, in case we get to that later in the unit. There are 4 types of transformations. We have reflections, rotations, translations, and dilations. A reflection is a flip, and this is stuff we've learned in junior high. A rotation is a turn, and a translation is a slide, and a dilation makes things bigger or smaller. So we'll look at each one of these individually in just a little bit throughout the next couple of videos. So right here, they just wanted to see if you could remember what they were. Name the type of transformation demonstrated in each picture. This one right here, we took and we turned it. We reflected it across the line, so that makes it a reflection. On B, we took and we turned it about a point. That makes it a rotation. On C, we took and we slid it, so that makes it a translation. And then this very last one, well, hey, that's almost like looking in a mirror. That is a reflection. So again, A was a reflection, B was a rotation, C was a translation, and D was a reflection. I need a lot more practice writing with these pens. Now, in transformations, we're going to learn about 2 things. A congruency transformation, which is a transformation that changes the position of the figure without changing the size or the shape. And an isometry, which is a transformation that preserves length and angle measures. So notice isometry, congruency transformation, they mean the same thing. They both just tell me that it holds its size and its shape, that the 2 figures, whether they're triangles, squares, rectangles, whatever you're rotating, translating, reflecting, they stay the same. Now in a dilation, they would not. So we're going to learn when we get to dilations that they are not a congruency transformation. They are not isometric because they don't hold the congruency in the figure. So moving right along into reflections. A reflection is a transformation that flips across the line of the pre-image. So again, my key word right here is that it flips. Now we've already been doing flips across the x-axis and y-axis, so we're going to look at one of those and then we're going to move on from there. I'm going to talk about the coordinate notation real quick. If I go about the x-axis, my point moves to where the y value changes signs. Just a real quick little picture. Here's my x-axis. My point was here. It moves down here. I went the same distance of x, but the y changed. Now that negative sign does not mean it has to be a negative number. It means that it changes its sign. A reflection about the y-axis. Here's my y-axis, so if my point's here, it would move over to right there. Notice the y values did not change, but the x changed signs. So on the x-axis, I changed the sign of the y. On the y-axis, I changed the sign of the x. Now what might be new to you is about the line y equals x. Y equals x, if you remember your algebra, is right down the middle. That's also known as our parent function for linear equations. I know we have an end of course coming right up, and that could be on there. So that is the parent linear function, y equals x. So if I take and flip it across the line, y equals x, what happens is I just change the values of my 2 points. And we will look at examples of some of the stuff. Y equals a negative x. Y equals a negative x is this line right down the middle going the other direction with that negative slope. That's my line y equals negative x. So I'm going to flip it across that line. So we will look at axes, we will look at horizontal and vertical lines, and we will look at reflecting things across y equals line, y equals x, and y equals negative x. So what I want you to do is go ahead and pause real quick, and we're going to look at this problem, and I just want you to take and transfer this arrow piece over here onto that arrow piece. I'm going to pause while I do mine also. Okay, so I drew my arrowhead on my piece of graph paper, and now I'm going to try using the thing, and I'm just going to talk about a reflection. If my line is 2 above, it needs to go 2 below. It then went 2 to the right, so I need to go 2 to the right. And then that one went up 2, so I need to go the opposite way and go down 2, and then I'm going to connect there. I have just done a reflection. I have my blue top half of the arrow with my red top half of the arrow. So that is a reflection about the x-axis. And I know that you have done those in the past, so I'm not going to spend a lot of time on those. Now we're going to look at what happens when it's x equals 3. Well, first of all, you have to remember about the line x equals 3. I'm going to try to color coordinate this, so I'm going to change that little red line into a yellow line for my x equals 3. So x equals 3 is my vertical line. So I have to remember that when it's x equals 3, it is a vertical line. I'm trying to use a thinner pen, so you're going to hear me tapping as I write. Now, I'm going to go ahead and pause for just a minute so I can plot my points, and you do the same thing. And I'm going to go ahead and plot the points in both graphs for now. Okay, so now I'm back. I've plotted my 2 triangles, ABC, on both of my grids right here. X equals 3 is that vertical line. So now what I want to do is I want to move each point. My A is 2 to the left, so I want to move it 2 to the right. So it'll move to right there. So that's my A. Remember, I call it A prime because it's the one I moved. B was 2 to the right, so I'm going to move it 2 to the left. And finally, C was 1 to the left, so I'm going to move it 1 to the right. So when I reflect this line across the line x equals 3, there is my reflection in red. I'm going to do the same thing with the next graph. Y equals 1 is a horizontal line. So I'm going to draw y equals 1 right here, horizontally, and then I'm going to take and reflect that point. Well, point A is 2 above, so point A needs to move 2 below. So there's my A prime. B is 1 above, so B needs to move to, whoops, sorry, I hit the wrong button. B needs to move to 1 below. I think I kind of got off a little bit on my counting right there. And C was right on the line, so C is going to stay on the line. If you're on the line, it doesn't move. So there is the rotation, there is the reflection of my new points. So if I've got a horizontal or a vertical line, I treat it just like I would an axis. It turns out to be just the same. It's shifted a little bit. Okay, on to reflections. I'm going to graph it across the line y equals 2. So I'm going to draw in that line y equals x right here. Excuse me, I said the wrong thing. Graphing a reflection in y equals x. So I'm going to draw in my line y equals x, and now I'm going to plot my points. And this time what they're asking me to do is reflect it across the line y equals x. And instead of being a triangle, all I'm going to be plotting is 2 little points. So I'm just going to be doing a segment. So I'm going to go ahead and pause while I plot those 2 points. So I plotted my little points F and G. Now I want to go ahead and I want to reflect them. So I'm going to go back and think about what is my rule. Remember, my rule for y equals x tells me I take and I just change the order of my points. So when I change -1, 2, it becomes F prime at 2, -1. And when I do the G, it becomes G prime at 2, 1. So now I'm going to go plot those 2 points. So I just went and plotted point F, and I plotted point G, and that's a reflection across the line y equals x. If I think about taking my paper, that's what a reflection is, and flipping it across the line, those two would land right on top of each other, the blue and the red. So now I'm going to look at what would happen if I have the line y equals -x. So that's going to be the reflection going right down the middle the other direction. And I have my 2 points. I'm going to pause and plot my 2 points. If you remember your rule on this one, it says you take your point, and when you reflect it across y equals -x, you not only switch the order of your 2 points, you also change their signs. -y, -x. So that means F is going to go to F prime. It's going to become a -2 and a +1. And G is going to go to G prime, and it's going to become a -2 and a -1. So I'm going to pause and plot those 2 points. So now I plotted my F point and my G prime points right here. Those are little primes. And I noticed, did you notice before it went from being a horizontal line to a vertical line, and the same thing happened when I went across the line y equals -x. We have a reflection theorem, shouldn't surprise you. That theorem says a reflection is an isometry. Remember, that means it holds its congruency. So if my segment is a 2 segment, it's still going to also be another 2 segment. So it will stay the same size and the same shape. Okay, so moving right along on to rotations. Again, if you need to pause at any point in time. A rotation is a transformation that turns a figure about a fixed point. The point on which the figure rotates is called the center of rotation. If you have a figure that you want to move clockwise, you take and you turn it this direction here, and counterclockwise would go the other direction. So you do kind of need to remember what clockwise is and what counterclockwise is. They kind of turn them in different directions. Rotations are a little bit more difficult for some people. They're somewhat harder to see, but I have all the faith that y'all will be wonderful on this. So I'm just going to look at a couple of examples of rotation and help you understand what the angle is. The clockwise rotation says I started here and I turned it in this direction. If I connect each point, I take this and I connect it to this, and I take this and I connect it to that first point, the corresponding points. Notice my angle right there. That sure looks like a 90-degree angle, and it is because it was a 90 degrees clockwise turn. If I look at this one, we're going in the opposite direction. And again, if I connect the corresponding parts right here, or even if I took and connected it clear to these other corresponding parts, my angle of elevation is 60. If I were to connect this dot to that dot and draw in my angle, it would still be the same size angle. If every time I connect those corresponding parts, that to the origin and this to the origin, I'm still going to have the same angle. In this case, a 60-degree angle. I would just ask you to be able to recognize and match the size of an angle. I won't ask you to draw anything other than a 90, a 180, and a 270 rotation. But you do need to kind of recognize the other types. So identifying whether something is a rotation or not, I'm going to stop and pause the video so I can plot my line AB and my line CD, and my AB and CD on both of these. So if you would do the same thing also. This is a little bit hard to see because these graphs are a little bit tinier, but basically what they're saying is if it is a true rotation, when I connect point A to the origin and C to the origin, I get that size angle. Looks pretty much like a 90-degree angle to me. When I connect B to the origin along with angle C right here, that also looks like a 90-degree angle. So therefore, is this a true rotation? Yes, it is a rotation, and I went 90 degrees, and I went from AB to CD, so I'm going 90 degrees in this direction, which makes it a clockwise rotation. If I go over here and I look at the next picture and I connect A to C right here, you can see I kind of get this. That kind of looks like a 90-degree angle to me because I'm kind of going to both. But if I connect the next one, connecting D right here to B right here, it's not the same size angle as the yellow angle was. Okay, my yellow angle was right in here, not the same size. So this one right here is not a rotation. Is this a rotation here? If I took this blue triangle and I translated it to the red triangle, would it be a rotation? So if I drew my angle from P right here to S, that's 180 degrees. So this is a 180-degree rotation. When I talk about a 180-degree rotation, if I connected other corresponding parts like Q to R right here, again, that's a straight line. When I go through the origin connecting those, that is again a 180-degree rotation. When you talk about 180 degrees, I could go clockwise, which would be this direction right here to get there, or I could go counterclockwise to get there. Either way, I've gone the same thing. So whenever it's 180 degrees, it can be a clockwise or a counterclockwise. Apologize for the bad handwriting. That's why you really have to listen when you watch one of my videos. I'm trying to learn to write with this pen. Okay, so I'm going to now talk about the coordinate notation for a rotation because some people really have trouble with it visually. So we have a 90 degree, which says I take the original problem, I change the order, and I change the sign on the Y value. 180 degrees, I keep it the same order, but I change both signs. A 270 degree, I change the order and I change the sign on the X this time. And then if I do a 360, I'm right back where I started, so I'm at the same spot. Now notice in this book, they have determined that they want to do these counterclockwise. So in the textbook, not on our worksheet, but in the textbook, the problems go in a counterclockwise if it's not stated. So if you're ever working a problem and it doesn't state which way to go counterclockwise. Now we need to do a little bit of thinking here. If I think of a graph right here, and I've got a dot here, and I go 90 degrees clockwise, how far have I gone if I go in the counterclockwise? 90, 180, 270. So all of these are counterclockwise. If I want to relate them to a clockwise turn, on a clockwise turn, my 270 is going to relate to a 90 degrees, and my 90 is going to relate to a 270 clockwise turn. And as we already said, when it's 180, it doesn't matter whether it's clockwise or counterclockwise, they're the same. The same is also true with the 360. Just wanted to show you real quick on here because if you're really good at memorizing, great, memorize these. If you're not really good at memorizing them, like sometimes I kind of forget what they are, this is how I do it. I take a graph and I put a dot on that graph. Now my particular ones are going to be not clockwise because that's what my little button says. I can rotate it. So my original figure, I'm going to do the 360 one. My original point right here was the point 23. That was my original point, 23. I'm now going to select my picture, and I'm going to take and I'm going to rotate it 90 degrees clockwise, which means that would be a 270 degrees counterclockwise. Notice what my new point is. My new point has the coordinates 3, -2. I went to the right 3, and then I went down 2. So it has the coordinates 3, -2. Notice how that relates to my rules. I switched the order, and I changed the value of the original X to being the opposite value. If I select this again, and I rotate it 90 more degrees counterclockwise, which is a 180 degree turn, notice where my point is. -2, I went left 2, and then I went down 3. Notice from my original 360 to my 260, I changed both of my signs. Everything else stayed the same. Let's just do one more quick rotation. If I rotate it another 90 degrees, that's like a 90 degrees counterclockwise. So if I count my point here, I went left 3 and up 2. So if I look at that relationship, I changed the order and I changed the value of the y. It was positive, it went to a negative 3. So that's how I do it if I can't remember my rotations. I just take a piece of graph paper, put a point, and I just rotate my paper to find out what the correct rule is. So I'm going to pause right here and I'm going to graph this figure that they tell me to graph. I find these particular problems much easier to graph by using my coordinates and using my rule. So my R, if I look at my rule, says change the order, so it becomes 1, and change the sign so it's a negative 3. That would be R prime. S prime, I'm going to switch the order and change the sign on the X. T prime, I'm going to switch the order and change the sign on the X. And on my U prime, I'm going to change the order and change the sign on my X. Now I'm going to stop and pause, and I'm going to plot those points again, and I should see a rotation of that figure that is 270 degrees about the. So now I have replotted it. I replotted all my red points, and that's rotation. I started here, okay, and I went 90, 180, 270 to get to right there. So that is my rotation going in it. There is another way to do it visually as well, and if you ask during class, we can show you the visual way of doing it. I like to show the coordinate notation so that the people that aren't good visually can do it, and if the people are good visually, then they don't need to know the rotations. The whole thing is, can you recognize a rotation, and can you take a figure and rotate it? We have a rotational theorem. I guess you can guess what it is. A rotation is an isometry, which again means that it holds its congruency. So far we haven't really showed what you would do with that. So here are a couple problems that kind of show what you might possibly do with the fact that a rotation is an isometry. This first one, they took the quadrilateral and they rotated about P. They want to know what the value is of Y. So what that means is, remember, it holds the same size and shape. So I need to look at my sides that have a Y, which is 7y right here, and I need to figure out what does it correspond to over here on this side, and it corresponds to that 4x plus 1. So I immediately want to write an equation, 7y equals 4x plus 1. I have a slight problem. Can I solve an equation with just both a y and an x in it? I can't. So what I need to do is I need to look at my figure and say, is there anything that might be easier to solve first? Well, right here, 3x is going to correspond to that 15 right there. Is that an easy equation to solve? You bet. 3x equals 15, so x is 5. Now that's not my answer. I don't go over here and decide my answer is h, okay? Now that I know what x is, I need to go over here to this equation and I need to plug in. So I have 7y equals 4, plug in that 5 plus the 1. So 7y equals 20 plus 1. 7y equals 21. So therefore y has to be 3, giving me the answer of G. Okay, my second example right here, just the same type thing. Find the value of R in the rotation of the triangle. So I want to find R. R is over here on this side. So I got to be able to follow my rotation around to see what the 4R corresponds to. And the 4R minus 3, if I follow it along, is going to correspond to the 3R right here. Those are my corresponding ones when I take my rotation around. So once again, I know that 4R minus 3 has to equal 3. It did not correspond to 3R. That was my mistake. That doesn't look right. I need to back up here. 4R minus 3 does not correspond to 3R. It corresponds to this side over here. So then I need to find another R. Well, there's this 3R right here. This 3R right here corresponds to this 2S plus 3. So I really needed to have the equation. Would have been easier that last way. 3R corresponds to 2S plus 3. Again, I have two different equations, so that means I need to look for something easier to solve. And if I look right here, 2S equals 12. If 2S equals 12, then what does S have to equal? S has to equal 6. And then I take it back up here and I plug it into that equation. So 3R equals 2 times 6 plus 3. So 2 times 6 is 12. I'm going to go right over here because I'm running out of room and getting super sloppy. So 3R equals 2 times 6 is 12 plus 3. 12 plus 3 is 15. Divide by 3, so R is 5. So my correct answer choice is B. Hope you have enjoyed these things about reflections and rotations. More to come on my translations and my dilations. See you in class.